slag and why we care. So let's start with the basic. What is the blast furnace slag? So as you can see, it is basically a tetrahedron structure of SiO4 with the silicon in the center and oxygen at the corners. So look at this diagram on the screen. You see a central silicon atom with a 4 oxygen atom at the corner. That's a tetrahedron. In the furnaces, these tetrahedron link together. Slag is really a multiple oxide system. It contains acid like SiO2 and Al2O3, bases like CaO and MgO, and even some sulfur, iron and alkalis. By the way, oxygen is the largest single element in the slag, about 40%. By the way, now why should we care? There is an old saying in the steel industry, if you take care of the slag, the furnace will take care of the rest. So that's not just a catchy phrase. Slag controls sulfur removal from hot metal, silicon content in the iron alkali balance, to avoid shell buildup, permeability of the body and stack. So every time you adjust flux, you are directly taking care of the furnace. So let's move on. So what happens if you add uh, no flux stone? Now imagine this. What if we ran the furnace without adding any flux stone? No limestone, no dolo. This gives us a real examples. Binary phase diagram, if you see alumina silica with a point uh, C mark a high temperature uh, uh, red zone labeled. So no flux, that is the solid slag. See the phase diagram. The vertical axis is the temperature, the red zone at the top is where the slag is solid. Without flux, our slag would come only from the coke ash, about 70 pound per ton of hot metal, plus pellet gang, another 170 pound per ton. So total slag volume only 240 pounds per ton. So, but here is the killer. The composition is 75 to 85% silica, almost pure acidic. That means melting point more than 2895 degree Fahrenheit. That is 1590 degrees centigrade, higher than the hottest part of the furnace. As for the viscosity is concerned, 10,000 parts, that's like cold molasses mixed with the sand. So what happened? The slag never really melt. It blocked the raceway. Gas cannot flow and the sulfur stay in the hot metal. That's the disaster. Operator yardstick is that's why you need at least 260 pound per ton of flux to get into the workable zone. If you see the furnace hanging or the slag looking like a dry rock, you forget the flux. Now coming to the acid versus base component. That is, so let's break down the players in the slag chemistry. So left side red leveled acid with the silica, alumina, iron icons. Right side green leveled bases, that is CaMgO, FeMnOK2O, and between them a tetrahedral network breaking apart as bases are added. So look at the left column. Acid like silica and alumina accept oxygen ion. They form long chain like tetrahedral network. So that makes the slag thick and high melting. Pure silica melt at around 3100 degree Fahrenheit with too high. On the right, bases like lime and magnesia donate oxygen ion. They break those chains. That's why adding CaO lower the melting point and makes the slag fluid in so in practice acid slag, that is high silica, melting point is more than 2800 degree Fahrenheit, very viscous, poor desulfurization is also there. As for the basic slag is concerned, CaO2 near 1.1, melting point 2450, viscosity 2 to 5 bars, uh, about as fluid as heavy motor oil, and excellent sulfur removal. So operator yardstick is your daily target is B2 between 1.05 and 1.20. That's the sweet spot. Fluid enough to drain from the hearth, but not so aggressive that it eats your refractory. Now coming to the engineered slag for blast furnace success. So if you can see so what does a successful blast furnace slag actually look like? So if you see, we have to always focus on the viscosity versus temperature curve. So here if you see these three lines, level, low, middle, high basicity, the middle line crosses 2 to 5 pass window at around toward 1450 degrees centigrade. Look at this chart, temperature on the bottom, viscosity on the side. The green zone between 2 to 5 pass is where we want to be, that at about 1450 degrees centigrade. For our target basicity, here our engineer recipe, that is 37 to 41 CaO, 37 to 41 SiO2, 7 to 10 alumina, 10 to 12 MgO. Slag volume typically 600 pound per ton of hot metal, depends on your raw material. Basicity ratio B2 is equal to 1.1 and B4 we aim as a CaO divided by SiO2 plus Al2O3. Also, critical FeO in the slag must be below 1%. Why? Because the blast furnace is good desulfurizer only when FeO is low. The basic oxygen furnace has a 15 to 25% FeO, which makes it a bad desulfurizer. So we do sulfur removal in the blast furnace, not later. Operator yardstick is every cast was the slag stream. If it ropes like hot cooking oil, you are in 2 to 5 pass range. If it pours like thick honey, increase your lime rate. So coming to our daily control yardstick, as we can see that so let's get into the numbers. You will use every shift. These are your yardstick. So table showing the B2 decreasing from 1.1 to 0.95, slag volume increasing, K2O removal going up but sulfur removal going down. So color coded red for the ores S removal, green for the better alkali removal, and this table tells a story. As you lower basicity from 1.1 to 0.95, you remove more potassium, that's good for preventing alkali buildup in the furnace wall. But you remove less sulfur, bad for hot metal quality. So you have to compromise. Here are the formulas you need. That is B2, P3, and B4, and slag volume in kg per ton of hot metal. So, but understand the conflict. Higher basicity, better sulfur removal, worse alkali removal. Lower basicity, worse sulfur removal, better alkali removal. So, operator yardstick is if hot metal sulfur is too high, increase B2. If you see alkali buildup, like shell scaps, decrease B2 and increase slag volume by adding more flux or changing ore blend. So coming to the end use and the operator's takeaway. Finally, what happens to the slag after it leaves the furnace? It's not waste, it's a valuable byproduct. Two paths from the BF taphole. Left path, slow cooling,